Hello, everyone, and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker's developed to help scientists discover the world around us. Today's topic is Total Reflection XRF. So this is something new. We haven't talked about it yet on the show, but it is related to XRF. So X-ray fluorescence, that's the technique where we use X-rays in order to excite new X-rays coming out of the sample. And based on those new X-rays that are coming out of the sample, we can tell and quantify the elements that are present. So this is a really important technique, not just in industry, but also in fundamental research, in understanding what makes up the world around us. To learn more about this technique specifically, though, we've got an expert here in the studio, and he's brought an instrument. So we're going to see it live working here. So with that, let's head on over and start our conversation. All right, good morning, Noah.
Good morning. My name is Noah Davison. I'm the application scientist for TXRF with Bruker. And today I wanted to talk a little bit about the S2 Picofox and TXRF in general and what it can look like for you in your lab.
So this is one of those techniques that if you haven't heard about it before, just, stay tuned and hear what we have to say, because I think it's really kind of game-changing in terms of doing trace element detection. That's really the specialist here, right?
Yes, absolutely. The joke is that TXRF, the T stands for trace. And what it actually stands for is total reflection, but it kind of stands for trace.
So now I heard about this technique about 20 or so years ago. I know we were having a problem in a lot of the fabs where we had aluminum coming in on silicon wafers. And so what they would do is they'd have these machines, and the ones we built, they were like huge. We actually called them goulash pot. It was so big. And you throw in a wafer, and then we'd be checking for just trace parts per billion of aluminum on that silicon. And the idea was, if you get any aluminum in a fab, it just destroys the entire process. You basically tear the fab down, and you got to rebuild. But this thing is not the goulash pot. This thing is much smaller, and that's quite surprising.
Yes, so TXRF is one of the techniques that was developed around the same time that XRF first came into existence.
Okay.
Yeah. Some of the earliest work was in, I think, like the 80s and 70s. However, as we got better and better detectors and better X-ray sources, we were able to take that technology, make it smaller, more convenient, and easier to fit inside of just about any lab.
So now, speaking of small, I don't see any special cables coming out of this thing. It looks like we just have a standard power outlet.
That's correct.
All right.
It is about 150 watts, and it takes standard outlet power. It doesn't require feed gases. It doesn't require any particular reagents aside than what's necessary to make a film.
All right. So if you want to take it off to the side of a mountain or something, you could run this thing off of your car. You could run it off of a generator. Even probably one of those battery packs that they have nowadays. You could probably run this thing, huh?
Yes. So the reason why I brought the Picofox in specifically is because if you look, we've got these carry handles here. We don't say that this is portable in the same way that handheld XRF guns are, but what this is luggable. So you can get it out to a field site, you can power it with portable power sources, and with just a little bit of alignment, you can get good results and then pack it up again and take it back to where you came from.
Yeah, and I guess when I think about that portability aspect of it, there's two scenarios. One being I'm going to take it over to the lake and check for contamination in the water. But then the other one is, I've got a product line, and I just want to have this thing on a cart with a battery pack that I can unplug, push it over the line, and do an occasional check.
Yeah, certainly. And you can accomplish that pretty easily with this. It's one of the big features of this is because we've got an X-ray source, a monochromator, a stage, and a detector. And that's about it.
All right. So now, when I think about trace elements, I'm going to bring up the elephant in the room, and that's ICP.
Yes.
So when I think of that, the standard is these really big tech instruments, and they require a pretty dedicated lab. You have to have a lot of sample prep. You have to have a chemist running the thing. How does this thing compare to using something like an ICP?
So these machines exist in approximately the same kind of measurement space as ICP, where we can get really, really low detection levels. We have a wide spread of elements that we're sensitive to. The significant difference is that our instruments are, of course, better in every single way.
Well, of course. That's what but come on. I mean, realistically, the people out there, they want to know. I mean, there is, some cases when one tool's right for the job and different tools are different. But when it comes to, say, looking at heavy metals, this is going to be there. What elements are we talking about here, qualitatively and then quantitatively?
Okay. So The big advantage for this machine over ICP is that it's small. It doesn't require all of that digestion and sample preparation. We're working with single drops of material. So the preparation, most everything about it is faster and easier. In terms of the element range we're sensitive to, we can hit most of the transition metals. The place where this really starts to see challenges is when you get into lighter elements like sulfur and lighter. Because what you see is this is an energy dispersive system. We use a silicon drift detector to measure the X-rays coming in. As you get lighter and lighter X-rays, it becomes harder to excite that atom because the X-ray just kind of passes right through it. And so until we change the laws of physics, that's something that is just not going to be quite as approachable. So we can still do it, but our detection limits are different.
And if we're looking at, say, quantification, heavy metals, bam, home run all day long. We're looking at those transition metals. We're also very, very good there. You start getting into that lighter stuff. You're talking about like magnesium. Detectable, absolutely. Quantifiable, we start saying depends. Right?
Your deviation gets a little bit higher. It depends highly on what kind of sample matrix you're working with. If you're looking at lake water, then we can hit a huge range very, very nicely. If you have something, like digested sediment from some, high concentration process, then things start to become a little bit more dependent on how you prepare the sample.
All right, great. So I think then we kind of understand how this fits relative to some of the other techniques that are available in the market. Let's talk about how this, though, compares to the other XRF techniques. I mean, because we just talked about tools like a Puma and a Jaguar. These are the benchtop machines too. But the samples, I know, they look quite different. They're typically kind of bulk more.
Yeah, so the bulk XRF that many people are probably familiar with, bulk XRF, you have a three-dimensional sample that you're interrogating. So the X-rays are hitting the sample, and as they move through it, what I always imagine is a flashlight being shown through a murky lake. So you have attenuation of this beam as it moves through. Parts are getting absorbed, parts are getting reflected, and all of those different interactions that are happening inside this three-dimensional volume need to be accounted for. These are those matrix effects that we use standards to measure for. But what if you could take that three-dimensional space and simplify it somehow? Like, for example, if you could take that lake and dry it until it becomes a two-dimensional surface. Well, now that it's two-dimensional, there is no more of that attenuation effect because we can treat it as if it were an infinitely thin film, and then all of those effects go away.
All right. So, I mean, speaking of that, we might as well talk about samples. So you got some kind of samples to look at here.
So here I have an example of one of the TXRF discs. It's 30 millimeters, and let me try and catch the light here. There we go. So that is an example of a nicely placed film on a TXRF disc. You can see that's about 10 microliters, so one single drop. In terms of sample preparation, really the thinner the better, the smoother the better, and the more homogeneous the better.
Okay, and so you use these discs. Now, what are those discs made of?
The discs themselves are made out of quartz, so silicon oxide. They are optically polished to be the perfect, most smoothest possible surface for X-rays to bounce off of, because background noise is the enemy of these machines. As soon as you start working with crystals or like silicon powders, things like that, so like geosamples or saline solutions, then we have to kind of take a few extra steps to bring down that background reflection. Otherwise, the trace signals that we're looking for get lost in there.
All right, so now the sample holder itself, now is that like a consumable or can you reuse it?
These quartz discs here are reusable. With just a simple acid and alkaline bath, we can completely clean the surface of them, and they're ready to be reused pretty much infinitely as long as you don't scratch them.
Okay, so as long as you don't scratch it and you can get off whatever you put on, because this thing is so sensitive that the parts per billion affect it.
Yeah, that is one of the more critical parts of using this machine is getting your sample materials clean again. The entire cleaning process, one of the more important parts is once I've got a set of discs that I've washed, I run the blank discs in the machine to prove that I've cleaned them properly, because it's very easy to contaminate something.
So then from that perspective, I mean, we're talking about low utility requirement. You just plug the thing in. We're talking about really, I mean, yeah, you might occasionally have to buy some new sample holders, but your cost of ownership, once you buy this thing, you don't have any ongoing costs.
Yeah, more or less.
And I'm guessing this thing then runs at a pretty low power, so you don't really have to replace the X-ray tube or anything.
Nope. Unless you're really beaten up on it and it fails somehow, the X-ray tube, we have units that have lived 16 years out in the field.
Oh, really? That long? This thing's been around? Wow, wow. So that's great. Now, talking about the unit, so we see it on the outside. What does a TXRF do on the inside? Like, what's the magic?
So on the inside, if we imagine that you have X-ray vision here, you would see a molybdenum source X-ray tube right here, and then there is a monochromator, which filters out everything except for just the 17.5 keV molybdenum excitation range that we want to use for our TXRF. Then there's a stage that just takes the disc and it holds it very securely in position for measurement. And 90 degrees above that, we have the silicon drift detector. So when the X-rays come in, they strike the surface, they excite our sample, and then the original X-ray beam is completely lost. It just hits the sidewall of the machine, and we don't care about that anymore. What we look at is only the fluorescence, and because we're completely off by 90 degrees, we have almost totally eliminated background noise.
So that's great. I mean, you don't have to, I guess you have to think a little bit about the Molly, but really most of it just goes right by.
Yes.
So we're not going to see some big Molly peak that we got to deal with.
Yeah, it's very, very nice.
Now, do you have to is it flushed at all, or is it evacuated, or anything like this?
You can get units that come with an atmospheric flush, but unless you specifically need that, you really don't have to have that.
Why would you need that?
For silver measurement specifically.
Okay.
Silver has an emission peak that is right next to argon in the atmosphere. And so there is a nitrogen purge that you can get for these machines. It'll get rid of argon, so that way you can measure silver. If you don't want to measure silver, you don't need it.
Yeah. Now, how sensitive is the thing? Like, do I have to align this thing every day, or does it?
No, not at all.
Okay.
In the vast majority of times, once it's set, it's pretty much ready to go.
Okay.
We have a couple standards that come with the machine. So you'll get a few multi-element standards, you'll get gain standards, you'll get sensitivity standards. Those can usually be run on a weekly to quarterly to annual kind of range, depending on what your particular quality assurance scheme looks like. But yeah, when you want to make sure that this is aligned, as long as you aren't picking it up and moving it around, it's pretty much set and forget.
I mean, it does sound a little weird to me. This thing is like the technique. It's very sound. I mean, it's a great method, simple to use. It sounds like the hardware is there. It's great from a consumable perspective. What do you think is like limiting the amount of adoption that we're seeing out there? Is it because there's not a lot of standards for it, or like ASTM?
So I think one of the big things that has harmed the adoption for TXRF is the fact that it kind of exists in the same space as ICP, and ICP is very well adopted by the community. Yeah. So many people, that when they go to work in a chemistry lab and they say, what sort of instrument should we get, they think about what they know. Yeah. So we try to get these into colleges and universities so that way people can get firsthand experience with them. The other thing is that when it comes to the very bleeding edge, we really can't do parts per trillion unless all of the stars have aligned, whereas ICP can. So that final decimal point, they still have us beat.
But I guess that's the thing that we find in a lot of techniques, like even X-ray microscopy, is that people tend to overestimate like that need. People
I would
like,
say so, yeah.
I need parts per trillion. Why do you need parts per trillion? Because it's a decimal place. Yeah, but the reality is, the problem you're trying to solve is on a certain order of magnitude. Okay, this solves that problem.
Yes.
And it does it in a way that's easier to use. It's more cost effective, easier to adopt. So really, this is a technology to go with. Now, I mean, anybody out there, by the way, I mean, we do it. I'm sure other vendors do it. If you ever have a need, you can always send them in. I mean,
oh yeah. I am always happy to run samples. It's quick and easy. Like you were saying, there are some other vendors out there. There's one that specifically makes designs that will hold a semiconductor wafer. Yeah. And in fact, the bigger version of this, the T-Star, has a tray that will specifically hold silicon semiconductor wafers for analysis.
So I would almost call this one of those golden opportunities for people. Because if you want to set up a lab to do this type of analysis, you're talking about low cost. You're talking about low running costs. You don't need to have any sort of training, really, or significant training for this. You can just set it up and be running samples for people.
Yeah, it's hard to overstate how useful
Yeah.
this can be inside of a lab. Not only can you use it for trace analysis of samples, but you can also use it for screening of your reagents. You would be very surprised how many times people would be buying ICP grade nitric acid and paying huge amounts of money for something where I can do analysis of histological grade, the $60 liter jugs, and they come out just as clean.
It's funny, I mean, because I don't know, my train of thought just evaporated here. No, but that being said, I mean, I think it's time to see this thing in action. I mean, we talk a lot about it. Is it really that easy?
Oh, I think it could be, but if only we had some sort of a sample here that we could test. Hey, would you look at that?
All right.
We've got some coffee right here.
Well, I hope that coffee doesn't have the arsenic in the apple juice or something.
No, I hope not.
All right, so you got a pipetter.
Yes,
so we need to have one of these.
An Eppendorf pipetter, 10 microliters. That's really all that we need to work with here. Because we're sampling this in qualitative mode, we're just looking to say, what can we see? We're not going to actually make quantitative measurements of it because we don't have any internal standard inside of my coffee.
Okay.
I like my coffee with cream, sugar, no gallium.
All right, so that's what you would normally use as gallium? You just put a little gallium in there?
Yep.
Okay.
So I would take like 1 milliliter of water, and then I would spike that with some amount of gallium, and then make sure it's well mixed, and that would be what I would actually sample for quantitative analysis.
So like if you wanted to boost the concentration of, say, heavy elements or something like this, would you ever like put it into one of those, I don't know, what's the name of the spinning thing?
Centrifuge?
Yes, a centrifuge.
You can play around with sample preparation methods like that. In fact, it's usually the other way around.
Okay.
So if you have, say, a geological sample and you want to screen for heavy metals, the silica in the geosample is actually something you don't want on your film because all of those silica crystals will increase your scattering. So what you can do is you can take your geosample, place it with a little bit of nitric acid to make all of the metal ions kind of mobile in solution, centrifuge all your powder to the bottom, and then take the liquid off the top.
All right. So let's go ahead. Now we're going to just take a little bit here.
So I have 10 microliters, and then with this slide right here, I place it on the sampling jig. That black spot in the center is the interrogated area. The X-ray hits it along a line, but the sensor is only detectable to that area right there. And I place a droplet, and then I put it on a hot plate and dry it.
Now, did you put the whole 10 on there, or did you just put enough to cover the dot?
That's the whole 10.
Okay.
Yeah, this is a little coffee coloring.
So that's simple. So that's just like suck it up, whoop, pop it down, and then put it onto a hot plate.
It really is that easy, yeah.
And then it'll look like that one.
Yes. So this one I've prepared ahead of time, and it's got. Try to catch the light. There we go.
That little.
It's got that lovely film formation there. So what we can do is I'll take this and I'll place it into my cassette here.
Oh, so you can actually load like multiple samples? It's not just one at a time.
Oh yeah. That sample cassette holds 25 discs.
Okay.
So one of the really great things about that is that if I want to, for example, run some samples overnight, I can set up 25 discs and then schedule a job to run all of them. It'll automatically go through each one, and then I come back in the morning and I have my results.
All right. How long does the measurement take?
Well, let's see here. If we switch really quick to take a look at the laptop, I manually tell it to load that disk.
Okay. I hear some motors going on here.
The little motor is grabbing it.
Yep. So does this thing need like a lot of maintenance for the motors and things like that? Or?
Almost none at all.
Okay.
And
wow,
now
wait a minute. So that's the live spectrum?
That's the live spectrum,
wow, that's fast.
So in the space of just a couple seconds, we're already getting something. You can see this large peak on the corner here is our molybdenum source.
Okay.
We can also identify silicon and argon from the disk and from the atmosphere. And then every other peak that we see on this spectrum is going to be something inside of our sample. Because nothing here is larger than our molybdenum peak, we really haven't saturated our detector, so we don't have to worry about errors, we don't have to worry about artifacts.
Yep.
Everything on there is something.
All right, so what's in the coffee here?
Well, let's pull up an elemental list here. I'm going to stop the collection so I can look at things a little bit better.
Now, to be clear, when we look at the results here, we're going to be seeing things that are like elements. We won't be seeing like, oh, there's a caffeine peak.
No,
right?
unfortunately, so the 17.5 keV, that energy range is enough to kick out an internal electron from one of the lower orbitals in an atom.
Yep.
So we don't get to see things like oxidation states. We
Yep.
don't get to see things like bonding.
Yep.
Instead, we're going to see nuclei.
Yep. And we see elements, not molecules.
Yes, exactly. So if I start taking a look at my spectrum here, oops.
So the measurement and the analysis software kind of all in one here.
Yes.
Okay.
So
what are we seeing?
I'm seeing potassium and a couple light elements here. Looks like calcium and titanium maybe. Rubidium is a little bit of an interesting one, but because there's a high concentration of potassium, it does make sense that there'd be some trace level of the other one behind it.
They're kind of like linked?
Yes.
Okay, so you typically see one and then you see the other.
Yep. So if you look at the periodic table here, rubidium is just below potassium.
Yep.
They have really similar reaction properties. And so when there's a high concentration of one, you'll tend to see the other.
Okay, so and that's not some sort of artifact, like that's a potassium secondary peak or something. That's legit, like, that's rubidium.
Oh, yeah. That's actually one of the big advantages for TXRF is, so like if I zoom in on this rubidium peak here, that was collected in 45 seconds. So it's a little bit noisy. But there is nothing else that this could be. If I take my icon and I kind of slide it across here, I can see in the finder as it tells me what particular elements have emissions in that range. And rubidium is about the only thing that could fit the peak of that range. On the far side over here is uranium, and on the far side over here is polonium. But if I have either of those in my coffee, I've got bigger problems.
That's true. But we could tell you if you have those things in your coffee.
Yes, exactly. But the really nice thing is that if you're looking at some kind of peak in your spectra and you say, what is this? As long as you have prepared a film properly and you're not looking at overwhelming amounts that the detector's getting saturated, then every single peak belongs to an element. And interpreting the spectra is much, much easier than it would be for bulk XRF techniques.
All right. Now, this system, then you said, has a Molly tube. That's why you kind of have that Molly peak. With this system, do you offer a different tube also, or is it just the one?
So for the PicoFox, we have the Molly tube, and that's the only kind of configuration that we've got. It's just one tube.
Okay.
For the T-Star, the big brother to this machine, we have two tubes that give us 3 different excitation regimes.
What's the second tube?
So the second tube is tungsten.
Okay.
Tungsten has a lower energy emission than molybdenum, and so it's better at exciting some of those lighter elements that molybdenum kind of just passes on through at 17.5 keV. But the emission for tungsten is closer to 8, which is a little bit less than half. And so we better excite those light elements.
All right. So now that machine, you say it's the bigger brother, but the reality is it's only like a little bit bigger. This isn't like the table side. This is like maybe twice as tall.
Bigger brother as in stronger and more capable.
Yeah. And that one also, though, doesn't require any special utilities or that.
Exact same. In fact, the best feature of the T-Star over the PicoFox is it has an auto-align button. So in the PicoFox, if I were to drop this and I needed to realign it, I would have to do that with some knobs and some careful time. For the T-Star, you press a button and it just does it itself.
All right. So even though there is a little bit of manual alignment sometimes on this machine, it's something's pretty straightforward. A user or a advanced user, we would say.
An advanced user could do it themselves. A basic user could get on the phone with us and we could walk you through it over the phone.
Yeah, I was kind of surprised because it's actually like under that door, right? Like,
you
just open the little door and.
So this little door here, if you press the button, it opens up and there's a couple knobs that will change the position of the stage and how the X-ray beam interacts with the sample. Under normal operation, you should never ever have to touch those.
Yeah, don't do
that. But if you start to have some kind of problem, it's right there in front of you. You can open that up and make some adjustments.
I mean, it's nice though because if something does happen, like you said, you knock it a little bit too much, something like that, you can do it yourself, and you know clearly what to touch. You don't have to take the top off and do all this. So now this was a qualitative example. Like you said, we didn't spike it at all, so we didn't have a known.
Yes.
But you do have an example of something that is a quantitative example we can look at, right?
I do. So if I look at, just recently I did a test of bromine in soda because the FDA recently banned the use of brominated vegetable oils in soda. So I did a whole bunch of these and I just went and bought every single soda I could get my hands on at the grocery store. and I tested a bunch of them.
Could you tell us all the flavors in the Dr. Pepper?
Yeah. So let me find a couple where bromine came out some. Here we go. So this is an example of soda that I dried down to a film, but I spiked it with gallium before I dried it. So what that means is that this gallium peak here is a known concentration.
Yeah.
And because we have fundamental parameters that tell us how much we can excite every individual element, we know the height of that peak, we know what that concentration looks like, and as long as we make the assumption that our sample was homogeneous and evenly mixed throughout the sample, then we can tell the concentrations of every other element we see. So, this region over here has a lot of the salts that are kind of involved in soda. So we have silicon from the disc, sulfur, chlorine, potassium, calcium. But if I come over here to this region, I have gallium and I have bromine. And these are the reason why I was so excited to do this analysis was because look at that beautiful separation.
Yeah.
It's right there. But that's why we like to use gallium, is because it's nicely separated from other elements and it's not usually in anything.
All right, and how long did that spectrum take?
This one I took 1,000 seconds.
Okay, so 1,000 seconds, about 15 minutes, and sample prep time, 5 minutes, something like that. So 20 minutes, start to end, bam, you got all the result.
Yep. 20 minutes is about the top end of what you can really expect to take for time, because when we start collecting information about the spectra, it's a statistics game, right? Because our silicon drift detector is counting individual X-ray photons as they strike the detector. As we collect, we're also collecting background information, and as you kind of go on, there's a certain point where you're no longer collecting any more signal to noise, and that point is right around the 1,000 to 1,500 second range.
All right. So, and you could always load up a bunch of samples, like you said. Bam, and then you go. And then T-Star, that holds even more samples, right?
Yes, this holds 25 in one cassette. The T-Star can hold 90 across 10 cassettes.
Wow.
And they are hot swappable. So with this one, you have to finish that job before you can start the next one. With the T-Star, you can load them up and start one and take out the old ones as you go.
All right. So with that, we're kind of going to get to the time where we answer some questions. So if anybody out there is joining us live, you can type them in the side of your screen right now, and we'll answer them. Otherwise, send them into live.events@brooker.com, and we will get back to you on that. Also, by the way, if you're ever watching or see a future live from the lab that you're interested in, you can send an email to that email address, and we'll get to the question during that broadcast. So we do have a few questions that had come in before, and the first one is from Adrian, and that's, what's the learning curve like for operators? I think you've kind of addressed it, but it seems really simple.
We talked about it a little bit, but the learning curve mostly has to do with all of the rigor that's involved in handling trace level analysis, because sources of contamination become more and more of a concern the less and less of a sample you're measuring and the more and more trace you want to get results of. But as far as interpreting spectra goes, when you buy a machine, it comes with a training session. In your lab that will do, usually it's going to be me.
You can have this guy come to your lab.
Exactly. I don't know if that's a selling point or not. But the training lasts for 2 days, and that's usually enough to cover everything from maintenance to interpretation of spectra, and then leave a little bit of time at the end for developing a method for you guys' specific material.
Yeah, I mean, that's a good point, though, about that contamination, because I know you were mentioning, like, even just like a gold ring or a gold piece of jewelry, you touch it. And...
Yep. That's my favorite demo to do, is if somebody's wearing some kind of jewelry, you can just have them rub it with their finger and place a fingerprint on a clean disc, and you can see the metals coming off of that.
Wow. So we're losing gold left and right. That's what I'm hearing there, huh?
Yeah, those atoms are just falling off everywhere.
Oh, my God. There's a new market. We've just uncovered a new market here. Okay, from Marvin, how does TXRF compare to ICP? When would you choose one or the other? So we've talked about that quite a bit. I think, though, if we get to that end question, when would you choose one or the other? Like, what applications does TXRF really excel at, do you think?
I think applications that TXRF really excels at are ones where you want high sample throughput, and ones where you're sensitive to the ongoing cost. Because TXRF is lower cost up front than an ICP machine, but it's also lower cost over time because you don't have those kinds of reagents. You don't have to buy big tanks of gas. You just get a machine and put it in your lab and start running.
All right. Yeah, and if somebody's interested in what one of these things costs, they can always just write out to us, and we can get you a quote on it. Have a conversation, make sure we get the right setup.
Yeah, exactly.
All right, Joanna had written, how can you achieve the best possible results? That is a big question.
Yeah, that question's given a couple hours of time during training. But the broadest possible way I can say is that as long as your sample is homogeneous, and as long as your sample makes a nice smooth film, that's going to give you the best results. Making the sample become homogeneous, we have a couple tricks to kind of get you to that point. And then making the sample become a nice smooth film, we also have a couple tricks that'll help, like a really saline sample or a geological sample, for example. Ways to make that smoother and perform a little bit nicer. But those are the two big things is, because you're only placing a single drop of material on that disc, you want to make absolutely sure that drop represents your sample, and then you want to make sure it becomes a nice film.
All right, so flat and shiny.
Yes.
That's the way to go. All right, and then Dalton asked, can you analyze biological samples directly, or do you need digestion? That's
actually a really good one. So we do talk about digestion, and digestion is a sample method that I recommend. But it's not the same kind of digestion that people are used to when they think of ICP. ICP digestion involves microwave digesters or maybe HF, which is really hazardous and not pleasant to work with. For me, digestion is room temperature. You take 10% nitric acid and put it in with your sample. That's it.
All right. And not the kind of digestion like that coffee that comes from those cats. Have you ever heard of that?
Oh, no.
Where like they eat the fruit, and then like you go and you collect what comes out the other end of the digestion. And then they make coffee out of it. It's very expensive. I don't know. Maybe it's the best thing ever. Maybe this technique could tell us why it's better.
Yeah,
I don't know.
I mean,
the fun.
If we were able to put it into a thin film on a disc, no matter what it is, we would have something to say about it.
There you go. All right, and with that, we've come to the end of our time. Thank you, Noah, for joining us on this episode. We look forward to learning more about this technique. We'll have you on again, and maybe we can see the other machine, the T-Star.
Yeah.
And thanks to everybody out there for joining us, spending your time with us.
All right. Yeah, thank you for having me. It's a pleasure. And if you have any questions at all about TXRF or things that these kinds of machines could do for you, reach out. We're always happy to find a new and interesting challenge for these things.
Yeah, and when you're looking for these trace elements, especially that parts per billion, it's really important to keep your signal high and that background low.
Yes.